Yeah. So first of all, thank you very much for the invitation and the opportunity to be here today. So I know it's the last talk after two very long days. So somehow they put the statistician always as last. So it's not my fault. I didn't do the planning. So thanks for sticking around. And so what I want to talk about is about the statistical learning. So about the recent trials. And they were already briefly mentioned. So I want to reflect on what happened earlier this year, and was this something that we can expect, or can we prevent this in the future? So I want to talk about the MLEC study, of course, the Utrecht ALS, and for there's a JR10 study. So those were very large phase 3 studies that failed in the beginning of this year. So what happened with these studies and why they initiated those studies was that they were preceded by positive phase 2 studies, and they were already briefly mentioned by the other presenters. So I've summarized here those studies for you in a table. So you can see the different rows are the three compounds that we're looking at, and then I've summarized of those phase 2 studies that preceded the phase 3. I've summarized the sample size, the follow-up duration, and the p-value. And you can see that all three of them had a significant p-value. And if we go a little bit beyond the p-value, we can also think about like what the effect size and what was now the treatment effect that was observed in these trials. And I tried to standardize that based on the data that was reported. And you can see it's about a 0.4 to 0.5 point gain in the ALS FSR per month. So if we would do a 6-month study, that would be like a 2 to 3 point gain in the ALS FSR. So if you compare the active to the placebo arm. And if we do a 12-month study, that would reflect about a 5 to 6 point gain in the ALS FSR. So that sounds quite relevant, and we can also express this as a percentage reduction as compared to the slope that was the discussion before. And then we can see it's about a 25% to 30%, even more than 30% reduction. So if we look at these results and we look at these trials, and you have a significant p-value and you have a 30% reduction in the ALS FSR, well, to me, that sounds quite reasonable, and of course it's clinically relevant if we can really reduce the progression rate by more than 30%. So I completely understand why they conducted then a phase 3 study. So I cannot present all of the data because not everything is public yet. So what I've limited myself now to is here on the third column is the results of the phase 3 studies that were released earlier this year. So we can see the sample sizes are tripled or sometimes times 4. We can see that all of the trials were much longer than the phase 2 studies. And what we of course can also see is that the p-value is nowhere near significant for the first one, and for the other two I can also tell you it's about the same direction as the first one. And what's maybe more surprising is that this 25 to 30% reduction that we observed earlier, that effect is no longer observed. So if you were present at the MND or at the NCALS presentations, for example, we could see that those lines are just basically laying on the top of each other, so there's no treatment benefit. And I think this is the main challenge that we need to address. And this is the question, so why is this replication failure there? So why can we not replicate the positive phase 2 finding into something in phase 3? So this is what I want to think about a little bit together with you. So how well, and that was my question, how well is actually predicting what we observe in the phase 2, how well would that predict the phase 3 study results? So for this, I thought about a little bit of an experiment. So what we can do is we can think about a hypothetical trial scenario. So we have just a group of patients, and let's say this is our phase 2, and we take a similar sample size as the JR10 study or the MLEC. We just simply randomize patients, so in this case it were 65, to active treatment or to placebo. We can follow those patients up for 24 months or for 6 months in this case, and then at the end of this 6 months we can calculate the difference in the ALS FSR or the difference in the progression rate. So we get this delta ALS FSR at 6 months. Now what I can do, because it's a hypothetical trial, I could also have considered, well, what would have happened if I continued that same trial for another 6 months? So the patients that were originally randomized to the active arm, I could just add another 6 months of active treatment, the patients that are randomized to placebo, I can add another 6 months of placebo treatment. And then at the end, so at 12 months, I can again calculate this difference between those two arms. And what my question is, and in order to understand a little bit about this replication crisis that we're in ALS, so how predictive is that 6 months delta FRS for the treatment effect that I observe at 12 months? So I presume it should be like almost 1-to-1, but if it's not, is it then maybe related to the outcome? And if it's 1-to-1 related with each other, so then clearly the reasons why those phase 3 studies related was not because of the outcome or the design, it was probably related to the drug or something. So I wanted to test this predictive value of 6 months for 12-month treatment effect. So we can think about a very simple experiment. So we have a very large trial we can take that was run for 12 months. So the EMPOWER study that ran from 2011 to 2013, randomized over 900 patients. So what we can do is we have this very large trial population, and we can just take a random sample out of that group and say, okay, this is my treatment group. And then I can take another random sample, and in this case I sample just 65 patients at random, and I say, okay, this other sample is my placebo group. And because I have the 6 months data and the 12-month data, I can just calculate what is the mean group difference in the progression rate or in the ALSFRS total score at 6 months, and I can do that the same for 12 months. And then I can use this experiment. So what does my 6 months data then tell me about the 12-month data? So you can repeat this. You don't have to do this by hand, but you have computers for this. So you can repeat it, for example, 10,000 times. And then what you can do is you can create a kind of correlation between what you observe at 6 months in the treatment effect versus what you observe at 12 months. And because it's just a random sample, there shouldn't be any difference between my hypothetical placebo and active arms, of course, but because there's sometimes variability, sometimes you sample a bit slow progressing patients in one group and faster in the other group, so you will see some kind of a distribution in those treatment effects existing. All right, so what do we get in the end is a graph. So here on the x-axis, or the horizontal axis, I will give you the percentage reduction that they observe at the 6 months data point. So if it's a positive number, it favors treatment, so it's slowing the disease, and if it's a negative, it favors the placebo, so it means the treatment is accelerating the progression rate. So I can do this for the 6 months, and then here on the y-axis, I have for the 12 months data. So in the perfect world, I would do a trial, and then I observe at 6 months, I observe a 25% reduction, and preferably at the 12-month data point, I would also see the exact same 25% reduction. Vice versa, if by random chance I have like a negative treatment effect, so if that's minus 25% at 6 months, it should also be minus 25% at 12 months. So these are the results of that simulation study that I talked about. And the good thing is you can see some kind of correlation. So there's a correlation between what we observe like for a treatment effect of 6 months with the 12 months. And you can see that whole cloud of points is centered around 0 because there was just a simulation where there was no treatment effect anyway. But what I'm a little bit concerned about are these dots here. So here, for example, those lower few dots, they suggest there is a 25% reduction at 6 months, but if I would measure the same patients for 6 months longer and then determine the treatment effect is all of a sudden 0. And you can also do that statistically. So we can test, for example, so how many of the treatment effects here in this random sample were significant and had a positive effect. So that happened to be here 267 significant findings. And then it would be interesting, so how many of those remained actually significant at 12 months? And there was only 130. So somehow I lost the other ones. They became insignificant at the 12 months point. So if we think about the predictive value, so the predictive value of observing a 6 months significant effect in this sample size, in this ALS-FSR data, it's only going to be less than 50% still significant at 12 months. So it's very low predictive value. And this was in the same patients. So you can imagine that if I do a completely new trial and then do a longer trial, what is that positive predictive value still? Well, it's going to be much lower than the 50% here already. So should we be surprised? We talked already a little bit about it. I'm actually not surprised because we know a lot about the ALS-FSR trajectory over time, about the natural history. And the main issue is that it's not a linear kind of trajectory. So on an individual level, it goes like up and down, it accelerates, it decelerates. And there was a couple of years ago a very nice paper from an Italian group, and they looked at the number of plateaus. So that means that a patient can experience a plateau during the disease course and then accelerate again, then have another plateau. And they looked at when do those plateaus occur. And this all happened between scores of 40 or 30. They had the highest probability of having a plateau. And that's exactly the population that we enroll in trials as well. So it could just happen that all the patients were in a plateau and then accelerated after the 6 months point. That's something that we've also shown in the Precision ALS, so this very large consortium in Europe, where we looked at the linearity of the ALS-FSR, and we showed that it's non-linear. And another problem is that there's wide patient variability. So even if we go, for example, only for the definite ALS, so that's something that the AMLEC study did in their phase 2, you can still see that red distribution there is quite wide. So there's still, even if they all have definite ALS, you can still see there's patients that almost don't progress and patients that progress very rapidly. So that is also nicely aligned with the talks before. So the thing now is that despite of having exactly the same patient, we know that the progression rate varies during follow-up, and because of that fact, and because there's so much variability and non-linearity, the treatment effect that we observe at one point is very poorly predictive for the treatment effect that we observe at the other point, at a later time point. And that can lead us to false positives. So if we see some significant finding at 6 months, but we know that less than half of them remain significant at 12 months, that is a false positive, basically. And in this case, they were all false positive. But it can also be the other way around. It can also be a false negative. So we can discard a drug or exclude something as potential treatment for ALS simply because it doesn't show a treatment effect at 6 months. But if we would have measured those patients longer, it could have been significant. So it goes both ways. So there's false positive and false negatives. And that's the problem of the follow-up time. And then there's, of course, the problem of the sample size. So this is just the distribution of the treatment effects that we observed at 6 months for different sample sizes. And you can see that in the black histogram, you can see that there were trials with a 50% reduction and a 50% increase in the progression rate. And if we increase that sample size, you can see that the probability of observing those kind of extremes becomes less and less. And what we often see in the ALS press releases, for example, is that there's a company and it says in a small trial, I found a trend and the p-value was less than 0.2, for example, and there was a favorable effect on the ALS-FSR, more than 20%. But actually, if you think about it, here could not have been a treatment effect. Here the truth is there is no treatment effect in the simulation. You can see that already 10% of my cases would have meet this criteria. So if we come back to this slide, I think what we can learn, it becomes quite obvious if we just look at the phase 2 studies. So these studies were short, and it goes primarily for the AMLEX and for the ADARAphone study. And if we look at the TATCA study, that had a good length, but it was very small in size. And I think this is the main issue here, is that these phase 2 signals on a clinical aspect have a very, very low predictive value, so both positive and negative for what's going to happen on the phase 3. So how can we improve? I think the main thing that we should do is to let go of this desire of determining clinical efficacy in small phase 2 trials. It's simply something that's not predictive. It's not going to help us. It's only going to cause false positives or false negatives. And I'm actually more worried about the false negatives, that we disregarding many drugs because they don't show a positive signal in a small trial. It can just be the variability of the ALS-FSR. So what I think that, and the previous speakers already briefly touched on that, so what I think is that we should really improve that go, no-go decision. So when are we going to initiate a phase 3? What do we need from that phase 2? And I think that should be based on biological efficacy. So we talked about like the biomarkers, so maybe like an NFL decrease, or that at least that you know that the drug affected the target. So is there target engagement? And then we can think about maybe about early stage outcomes, maybe like electrophysiology, NFL could be another one, and hopefully those, but there's not much knowledge about that yet. So maybe those kind of outcomes show much less variability over time. So what we observe at 3 months might be very well predictive for what we observe at 12 months. So I think that's a very important aspect. And then if we want to look at clinical efficacy, I think we should try to let go of that desire to do that in phase 2. But that just simply requires longer and larger trials. We have been talking also in the morning again about like the large variability in disease mechanisms and clinical heterogeneity. So if we want to measure something that's efficacious, you just need to have a longer trial, a larger trial. That's just how it is in ALS. And related to that is that we also often overlook that the gold standard, in my opinion, is still survival. Because the ALS-FSR has its own limitations. It doesn't measure cognition, it doesn't have the BMI, it doesn't have neurofilament in it, and a drug can improve any of those 3 compounds over those 3 aspects, and you will not see a change in the ALS-FSR total score. So I think that if you want to go for clinical efficacy, you should at least, it's fine to design the trial for ALS-FSR, but keep in mind that the trial should also be designed to detect a survival benefit. So a 12-month study might then still be not the most efficient way to go. Another aspect, I think, is that we should try to think about the harmonization of the designs and about the statistical analysis. So the Centaur or the Amylyx trial and the Adarafone trial, they were designed very similarly. But you can see that the TATCA trial was, again, very different from those. And then usually we end up with the question, so did that drug really not work because of something we changed in the design, or was it really the drug? So trying to harmonize the design, if we always use the same design template, at least we know it cannot have been the design, it's probably something related to the drug. And that's something that we're trying to do in TRICAL, so to make templates for example, phase 1, phase 2, phase 3 trials, and harmonize the statistical analysis also. So any variability that you observe in treatment effects can only be because of different efficacy of the drug. So I would like to finish here and thank everyone who's involved in TRICALS. I just noted that I think the French organization was not included in this slide, so I just realized too late. But luckily I see that the logos are behind me, so that's thank you very much.
So thank you very much. So now it's time for discussing the 3 papers and the 3 presentations. In the meantime,
the question here.
Okay.
Yes, very nice study, but you took statistical perspective to say that if there is no replicability, it's a matter of statistical artifact, since you said that if the phase 2 is efficient and phase 3 is negative, you say that phase 2 is a false positive. But I mean, if we consider that the effect of the drug depends on the biological mechanism, you can consider that's not the same biological mechanism after 12 months. So I shouldn't say that it's necessarily a false positive, just because the mechanism of the drug. So I think that we have 2 different points of view. I mean, one is statistical, but the second we also have to consider the biology.
Yeah, no, that's a very good point. It's not only a statistical issue. I think the main thing is that if you see an effect at the 6-month study and that then disappears, that could be, of course, like due to the biology of how the drug is working. But then, so in the EMA guidelines, they make this nice distinction between like disease-modifying drugs, so that must be like a persistent benefit of a drug over the entire disease course, or for example, symptomatic effect. So it could be that, for example, Amylyx or ADR10 have a symptomatic effect that maybe wears off after 6 or 7 months, and then the groups just catch up again. So on a disease-modifying term, so if it prolongs survival, that might not be the case then.
Just in terms of the 6 versus 12 months, how would open label extension affect that ratio? Would it have an effect? Because that's what usually happens with an open label extension.
Yeah. There's a danger in the open label extension as well. So if the drug works immediately, and then if I switch over all the placebo patients to an active drug, the net benefit that you get is that you start to dilute your drug effect. So then you expect the highest difference at the last time point that the placebo was still a true placebo. So I'm a little bit hesitant to it, but there's also some evidence that there might be like a delayed drug response that could also be. So that you first, and I think that's quite, from a biological perspective, is also quite logical, so that you, for example, the first time that a treatment can have a clinical benefit is, for example, after 3 or 4 months, because it takes some time for the drug to affect the clinical mechanisms. So it might first affect a biological mechanism, which later translates to clinic.